Consider the material dispersion. Pulse broadening due to material dispersion results from different group velocities of the various spectral component launched into the fiber from the optical source. It occurs when the phase velocity of a plane wave propagates in the dielectric medium varies non-linearly with wavelength, and a material is said to exhibit material dispersion when the second differential of the refractive index with respect to the wavelength is not zero, that is d2n d lambda square is not equal to 0. The pulse spread due to material dispersion may be obtained by considering the group delay tau g in the optical fiber, which is the reciprocal of the group velocity Vg. Considering n1 is the refractive index of core, we can write tau g equal to d beta by d omega, that is 1 by c into n1 minus lambda dn1 d lambda. The pulse delay Tm due to the material dispersion in a fiber of length L can be written as Tm equal to L by C into n1 minus lambda dn1 d lambda. The material dispersion tends to 0 in the longer wavelength region near 1.3 micrometer for pure silica. So if we perform some experiment on pure silica glass, you can see the dispersion actually varies in this way with wavelength, right? So at 0.8 micrometer we have large dispersion. At nearly 1.3 micrometer we have zero dispersion. This is the zero dispersion line, and at 1.6 or 1.7 micrometer we have negative dispersion, right? So this region where we can neglect the effect of dispersion, this window. This provides an additional incentive other than low attenuation for operating at longer wavelength where the material dispersion may be minimized. Also, the use of an injection laser with a narrow spectral width rather than an LED as the optical source leads to a substantial reduction in the pulse broadening due to the material dispersion even in the shorter wavelength region. So that is why actually 1.3 micrometer was chosen first. Later on we will discuss it later on when we can shift the dispersion characteristics towards 1.55 micrometer. The whole wavelength was shifted to 1.5 micrometer region, but previously 1.3 micrometer region was chosen as we have a window, low attenuation window right here. At the same time, dispersion near this region is also negligible. Now we consider the waveguide dispersion. The waveguiding of the fiber may also create chromatic dispersion. This results from the variation of group velocity with wavelength for a particular mode. Considering the ray theory approach, it is equivalent to the angle between the ray and the fiber axis varying with wavelength, which subsequently leads to a variation in the transmission times for the ray and hence dispersion. For a single mode whose propagation constant is beta, the fiber exhibits waveguide dispersion when d2 beta d lambda square is not equal to 0. For multimode fibers where the majority of modes propagate far from cutoff are almost free of waveguide dispersion, and it is generally negligible compared with material dispersion of the order of 0.1 to 0.2 nanosecond per kilometer. With single mode fibers where the effect of different dispersion mechanism are not easy to separate, waveguide dispersion may be significant. That is for the single mode fiber. For single mode fiber, what happens? The wavefront, rather if you consider the mode field diameter or mode field distribution inside the core may be like this. That means field distribution is highest here, then it will fall, and some of the field are still present inside the cladding. Okay, so we have two type of pulses, right? One is the core pulse moving through the core, and we have cladding pulse moving through the cladding, right? But since we have variation of refractive index in core and cladding, the core pulse is slower because core refractive index is higher and cladding pulse is faster, right? So at the receiver side, when both the pulses will come, they will come at different time, right? So it will come faster, it will come earlier, and this one will come later, so resulting in the broader pulse, right? Instead of this narrow pulse, we will get broader pulse.